Well, today I'm going to prove the Riemann mapping theorem, so that's exciting. I've been building up to this for a long time. We have all the ingredients we need now that we have Montel's theorem, Hurwitz's number 2, and the Schwarz lemma. Those are really the main ingredients. So there's the statement. If omega is the whole complex plane, then Liouville's theorem would show that every analytic mapping into the unit disk would be bounded and therefore constant. So omega unequal to the whole complex plane is clearly required in this thing. But if omega is not the complex plane and is simply connected, meaning no holes, then the famous theorem is there exists an analytic mapping from omega to the unit disk that's one-to-one and onto. And so we know that such a map, its inverse would also be analytic. And we know that such maps are conformal. So any simply connected domain not equal to the whole complex plane is conformally equivalent to the unit disk. That's the big result. And to even ask yourself if you could find a continuous mapping that does that would be a challenge. So the fact that it's not only continuous, it's infinitely differentiable and conformal is a really astounding fact. So the lemma I mentioned at the end of last lecture, a technical point, we're going to be dealing with a class of functions that are analytic and map into the unit disk and are one-to-one. Okay? It's important to know there is such a thing. If omega is bounded, it's clear because you can just take z divided by m for a big enough m and get a bounded function that's one-to-one into the unit disk. But if omega is unbounded, then we have to think about that. And I don't want to do that before I get rolling here, so I'm going to save the proof for later. It's a consequence of an easy consequence of the fact that if you can cook up analytic square roots on a simply connected domain. So if it's g is an analytic and non-vanishing function on a simply connected domain, there's an analytic g, so that g squared is equal to capital G. Okay, that's all that construction requires. So I'll save that for later, when I have enough time at the end, I hope. Okay, so that's lemma 1. There's a couple of little lemmas that I'm going to need an easy one. Lemma 2. It's a remarkable fact about analytic functions that if you have a sequence that's analytic on a domain omega, and the fn's converge uniformly on compacts to something, which of course would be also would be an analytic function, then not only that, but all the derivatives converge uniformly on compacts too. So fn kth derivative would also converge uniformly on compacts to the kth derivative of f. Of course, we know f is analytic, so it has a kth derivative. So that's a really strong thing, and it's way false R to R. I guess there's lots of things. We know there's an infinitely differentiable function that converges to a nowhere differentiable function. So that famous function is hn of t equals sum n from 1 to capital N. This is Weierstrass's version of smooth functions that converge to a nowhere differentiable function. So they start wiggling like crazy. And the wiggling is very steep in spite of having small enough coefficients in the front that make it converge uniformly. So that would converge to a continuous nowhere differentiable famous function. Continuous nowhere differentiable. And when you start thinking about that, you can come up with easier examples. Or how about just 1 over n sine 2 to the nt is easier to see that those derivatives don't converge uniformly in spite of the function converging uniformly to the zero function. Okay, the proof of that's just the Cauchy integral formula. So let's see, my favorite picture for doing something like this is that we have Fn like on a bigger disk. Then we shrink down. We're going to take the integral along on a circle, the green one here. Let's call that C sub r. And then we're going to take an even smaller circle of radius little r. Okay, so that's going to be a C sub little r. And we're going to look at the derivative inside that littler circle. So f is going to be analytic on the big circle. And so when I look at those derivatives, let's see, I'll have fn kth derivative at z minus fn f kth derivative. Let's say I won't put the absolute value modulus just yet. By the Cauchy, the higher order Cauchy integrals, that's k factorial over 2 pi I integral around C sub r of fnw minus f of w over w minus z to the n plus 1 dw. Okay, now let's see, the w in this integral is going around the C sub capital R. And so w and z stay away from each other. And it's the good old capital R minus little r distance. That's the closest they can possibly get together. And so now I'm going to take the modulus and get that this, by the basic estimate for integrals, is less than or equal to k factorial over 2 pi. And then we get the maximum of fn minus f, that's the function in there, on C sub r. And what's the maximum of the other stuff? The other stuff would be 1 over r minus little r to the n plus 1. That's the smallest that term could get. And then finally the length of the 2 pi r. Okay. And so because of uniform convergence on compact, this goes to 0 by uniform convergence on the compact circle. So that shows the fact on the little blue circle there, little blue disk. So if you're given a compact K, let's see, there's a symbol for K being compact in omega. Some books like to write it like that. So if it's compactly contained in omega, then you just cover K by blue circles. Blue disks, like above. And then you take a finite subcover. Questions about that? Okay. I don't know if I gave you this next thing as an exercise. Maybe I didn't this year. this next lemma is kind of like a Schwartz lemma. So this is lemma number 3, and I'd call it Schwartz number 3. I know how to spell Schwartz. Schwartz number 3, kind of. And it's about analytic functions that map the unit disk into itself. And F is analytic. But we're not going to assume that F of 0 is equal to 0. And so we don't get the usual number part A, but it turns out that the part B is still true, that F prime of 0 is less than or equal to 1. And if F prime of 0 equals 1, then F is a rotation. Has to be a rotation. With the modulus of lambda being 1. Of course, lambda is a constant. Okay. Well, the proof of that's going to be real simple. We already know Schwartz, so what we know now that we didn't know back when I could have done this is about the Möbius transformations, the one-to-one onto maps of the unit disk to itself. And that's what we need here. So let's see, I'm going to have, the picture here is, I'll have an F that's going to map the unit disk into the unit disk. Okay, so that's F. And so here's the unit disk. And it maps into the unit disk. So it could map to a blob that looks like this maybe. And it doesn't have to map 0 to the origin. So here's B maybe. 0 gets mapped to B, let's say. But in order to use the Schwartz lemma, I need my mapping to map 0 to 0. So the next map I'm going to use is going to take B back to 0. Or not back, but to. So it's going to take B to 0. And let's see, then that weird blob would get mapped to something like this. Maybe. No, B is in there, I'm sorry. B is going to be in the orange blob, but it's not onto it. Okay, so we get that picture. And let's see, that's phi sub B, this map. Phi sub B of Z is Z minus B over 1 minus B bar Z. We know that's a one-to-one onto map of the disk to itself, analytic. It's one of the automorphisms, it's a Möbius transformation. Okay, and so that satisfies the hypothesis of the Schwartz lemma. So Schwartz gives us that. Let's see, the composition, phi sub B of F of Z, derivative, I'm sorry, phi sub B composed with F derivative at 0 is less than or equal to 1. And so when I do the chain rule, that would give me phi sub B prime at F of 0. F of 0 is B times F prime of 0 is less than or equal to 1. And you can calculate that derivative. It's an easy thing to calculate. This, when you do the quotient rule and do some algebra, is 1 over 1 minus the modulus of B squared. And so what we get now is that f prime of 0 is less than or equal to 1 minus b squared. And of course that's less than or equal to 1. So check. We got that part. And notice if it was equal to 1, if f prime of 0 equals 1, then of course that b would have to be 0. And so f of 0 equals 0, and that would give me the Schwarz lemma. We have Schwarz. Which would say that if that maximum derivative occurs, then it's a rotation. So that's all there is to that. Questions? That's kind of a nice thing to know. Okay, now let's see. So let's see a corollary of this little lemma. If f maps the unit disk into itself and is not one-to-one, I mean, sorry, and is not, what am I saying? I won't worry about that right now, sorry. I'll save it. Okay, now I'm going to prove the Riemann mapping theorem. Drum roll. So I mentioned I'm going to let F be the family of holomorphic analytic, I guess I say in this class. The family of analytic functions on omega mapping. Important thing here is one-to-one. That's going to greatly simplify the proof. To have these be one-to-one, then I can use Hurwitz. Mapping one-to-one into, not onto, but into the unit disk. Okay, our lemma above implies that F is not empty. Lemma 1 implies script F is not the empty set. That's important to know. Now you can pick any old point in omega. So let's pick one. A is going to get mapped to the origin in the Riemann mapping theorem. Okay. And so let's let M be the soup of the derivatives of the modulus of the derivatives of the functions in script f at A. Okay. The first basic step is to say that M is finite. So step 1, M is finite. And that's an easy thing to see. Let's see why. Oh, here's omega. Let's see, we're mapping to the unit disk. So here's A. And we've got a map H rather, that maps into the unit disk. So maybe it takes like that. Okay, so it's just going to be the Cauchy estimate on a little disk like this. So I can stick a disk that's compactly contained in here. Let's say it's omega's open, So there exists a DRA closure contained in omega. And then you do the Cauchy estimate, the first order Cauchy estimate for let's see, it's that H prime of A, remember, is less than or equal to the max. Let's see, 1 factorial, the max of the thing over r to the 1. So that would be the max of H on that little circle. On that little circle, C sub r. C sub r A. That's C sub r sub A, super A. Okay, and so that's finite. And in fact, if you let that, you can let that r go out to the biggest it can get. That's the distance from A to the boundary. So here's a little remark. I can let r increase out to the distance to the, so increase to the distance from A to the boundary of omega. And so what you get when you think of it in those terms is that H prime of A. Oh, by the way, the max, this max is less than or equal to 1 because it's mapping into the unit disk. So I get 1 over r there. So this is the unit disk. And so this is actually less than or equal to 1 over the distance from A to the boundary of omega. But we don't need anything that refined. So that's easy. So now that step 1 is out of the way. Step 2 is take a sequence. We're setting ourselves up to use Montel here. Let's take a sequence H sub n in our class with H sub n A prime tending to my soup. Exciting thing now is Montel's, since the Hn are bounded, since the Hn less than 1 on omega, they're bounded, of course, on compacts. They're bounded on they're just bounded, period. So I don't have to say on compacts. Montel's theorem implies there exists a convergent subsequence. Subsequence HNK, which converges uniformly to something. Let's call it capital F on omega. And we note here that that limit has to be analytic. We knew a long time ago by Montel's that F is analytic. So my claim is that F is going to be the Riemann map. F is the Riemann map. I'll explain what I mean when I say the Riemann map. Right now I'm saying it is a Riemann map. Okay, so let's see. That's step. Is that? Now we're on step 3. Today, lemma number 2 implies that let's see, the HNK derivatives at A modulus tends to M. I mean, it tends to the soup. Well, let's see. What does it imply? Lemma 2 implies that this is going to tend to F prime of A. And so, F prime of A is the max. This is why we expected to get the Riemann map by maximizing that derivative among one-to-one functions. So that soup is, well, let's see, I got to show you that soup is actually a max. Something to note, F prime is equal to M, and M can't be equal to 0. And that's because a one-to-one function has a non-vanishing derivatives. One-to-one functions, analytic functions. This is something that was kind of a special inverse function theorem. So that was important. Because one-to-one analytic functions have non-vanishing derivatives. Okay, and so that means that F is not constant. So F is not constant. That's important because remember Hurwitz's number 2 said the limit of one-to-one functions is either constant or it too is one-to-one. So Hurwitz's number 2, I guess this is step Hurwitz's number 2 implies that F is one-to-one on omega. So we're feeling like we're getting somewhere. I claim that, let's see, so this is step 4. I claim that F is actually in script F. Let's see, we know that F is one-to-one. We know it's analytic. What we don't know yet is that it maps into the unit disk. So we just need to show F maps into the unit disk. Well, let's see. How do we know that? That's easy. Let's see. All the HNKs are less than 1. So the limit is less than or equal to 1. So F is the limit. Let's see, F of Z is equal to the limit of those things, h, n, k, z. Those are all less than 1, so that's going to be, limit's going to be less than or equal to 1. Okay. But if f of z was ever equal to 1, the maximum principle would imply that it's constant. So, but if f of z equals 1, let's pick a point, then the maximum principle would imply that f is identically constant. But it's not. It'd be a constant of modulus 1. And of course it's not, so that's a contradiction. So it's less than 1 and we get what we want. F maps omega into the unit disk. And that's the last thing we needed to see that it's in script f. So that means m is not a sup, it's a max.
Maybe I missed this, but how do we know f is surjective?
We don't.
Okay.
I'm not done yet. That's an important part. So let's see, the max of h prime of a, such that h is in script f. That sup is a max, because it's assumed, which is an interesting thing to know. Okay, the last step is that f is onto. And that's going to be another Schwartz lemma, and a clever use of Schwartz lemma. So that f is onto d10. Okay, let's suppose not. I'm going to start drawing pictures now. It's kind of like those pictures I did in number 2. So I've got a simply connected blob. It doesn't have to be bounded, but every one I draw is bounded for some reason. This is my omega. I've got a point A. And let's suppose it's not onto. Okay, then I have my F, and it's going to map to the unit disk. And it's not onto. So it maps to some kind of blob. And it misses W naught, let's say. So that means if it's not, then there exists a W naught in D10 minus F of, capital F of omega. Like in the picture. And now I'm going to start messing around trying to get a function whose derivative is too big. I'm going to get a function whose derivative at A is even bigger. And it's 1-to-1 and into. If that picture was happening. Remember, F has the biggest possible derivative. And if this happens, I've got to play a game and get something that has a strictly bigger derivative. Okay, so the idea is, let's see, I bet I can make the derivative bigger if I had a map that mapped to the, let's see, I'm going to take phi sub W naught of Z is Z minus W naught over 1 minus W naught bar Z. That's going to map to the unit disk, and it's going to move W naught to the origin. And my stuff that where omega gets mapped, some blob like that. Okay. Interesting. Notice that the composition there is non-vanishing. Notice that phi w naught composed with F is non-vanishing on omega. So it has an analytic square root because omega is simply connected. So we know there exists an analytic square root. Function. Let's call it little g on omega with g squared of z equals this composition. So that would be phi w naught of f of z. So note, let's see, note, things to note. G of z is less than or equal to 1. I mean, in fact, it's less than 1. G of z squared is that thing is less than 1. And of course, that implies that g of z in modulus is less than 1 on omega. So G maps into the unit disk. I'm going to mess around and show you it has a bigger derivative at some point soon. So it maps omega into the unit disk. I claim it's 1-to-1. G is 1-to-1, so in F. Script F. And the Y is easy. It's because G squared is 1-to-1. So let's see, Y. Let's suppose we had if G of Z1 equals G of Z2. Then their squares would be the same, of course. And remember, let's see, what that would mean that phi w naught of f of z1 equals phi w naught, this is kind of silly maybe, of f of z2. But phi naught, the phi sub w naught is 1-to-1 onto, so that means that f of z1 equals f of z2. I guess I'm just using the fact that the composition of 1-to-1 functions is 1-to-1 here. And so z1 equals z2. Because these things are 1-to-1. Phi sub w naught's 1-to-1. Okay, so that's easy. Okay, so, oops, I'm not done yet. The steps here are easy, but what do I have so far? I got to go back and draw my omega, the potato. I got an A. Okay, let's see. Remember what I had, my G in the picture. That's my G squared is that composition. My G squared is never 0. So, yeah. So, G is a square root of that thing, and it's never 0. So, what's the picture? My G is going to look like this. G is going to map into the unit disk. Oops, what was my G? Yeah, my G. Okay, so I take the square root of that thing. And the square root of that thing misses the origin because it's never 0. Okay, so my blob here is going to be, when I take square roots, it kind of it would half the angle kind of. Anyway, so it probably would close it down a little bit. It's not the same blob as before when I take the square root. But the blob, at least it doesn't include the origin. Okay. And now, let's see, B would get mapped to some blob. This is, let's say that G maps A to B. So B is equal to G of A. One more thing to do is to move B to the origin. So I'm going to take phi B of Z is Z minus B over 1 minus B bar Z. That's going to map that picture to the unit disk, and now B is going to get mapped to the origin. So that B is going to get mapped to the origin, and my blob now is some blob that contains the origin. Okay, so the drum roll. Okay, so phi sub B composed with G is in F, and its derivative is too big. And phi B composed with G prime at A is bigger than M. And of course that's a contradiction because M was the max. Okay. Okay, so that's a contradiction, and that means we were wrong when we said there's a W naught. So no such W naught exists. And that means that F is onto. Okay, and so let's see how to. We're going to be done. Okay, so let's write. Here's why. It's Schwartz. Clever use of Schwartz. Let's write F twiddle. It's going to be this thing with a bigger derivative. So it's going to be phi sub B composed with G. Okay, so let's check. So that means that let's check. You check. Check that. Let's see. F. When you go back and look at all the definitions, F is our original F is equal to a capital G composed with F twiddle, where my G, when you look at it and unwind it all, is equal to phi sub W naught inverse composed with the square function composed with phi sub B inverse, where S of Z is Z squared. It's a square function. Okay, so that's an analytic mapping of the unit disk into itself. So it's analytic, and it maps the unit disk into itself. And so the lemma says that G prime of 0 is less than or equal to 1. The Schwartz lemma number 3 thingy. What lemma was that? Number 3? Lemma 3, the Schwartz one, Schwartz number 3, implies that G prime of 0 is less than or equal to 1. And in fact, it has to be, so that's, I'm using the part 1 thing. And it couldn't possibly be 1 because if it were, that thing would be 1 to 1, and it ain't. Can't equal 1 because if that thing were just a rotation, it can't be 1 to 1 because G is not 1 to 1 because of that square function. S of Z is not. The other two are. Because G is not 1 to 1, because S of Z is not. So G of Z couldn't possibly be lambda times Z. Okay, so that we know that G prime is strictly less than 1. That's the important thing. So G prime of 0 in modulus is strictly less than 1. Let's put that in the box. That's a very easy thing to do because that's a very explicit map. I could even compute it to demonstrate that because it's just Möbius transformations and a square function. But the Schwartz 3 gives it quickly. And so finally, what do I have? I have f prime of A. It was that composition, so that would be equal to G prime of f twiddle of A, which if you look at my construction of f twiddle, that's equal to 0 and times f prime of A. F twiddle prime of A. That's just the chain rule. And so I get that f prime of A, which is the max, that's equal to m. That's equal to G prime of 0, which is strictly less than 1. And of course, it can't be 0 either because when a factor of it is multiplying to something that's not 0. And here I get f prime of A, twiddle. And we conclude that this must be bigger than m. And that's the contradiction. So F is on to. So I can fit proof of the Riemann mapping theorem into 5 pages once I have all the ingredients. And, none of them are really hard, but whoever figured out this proof was very clever. Their proofs have existed starting with, who did the first one? Was it Gauss? Maybe. I used to know that. Anyway, everybody's coming up with proofs, and Purdue came up with a constructive proof involving limits that uses these ingredients, but it's harder to explain. And this started